Hey guys, we're going to look at an example of how to calculate the equilibrant force. The equilibrant force is a force that balances all other forces acting on an object to keep that object in equilibrium. This example is about Kayla, the distressed dog walker. Now here's Kayla, and she's being pulled in 3 different directions. Tonto pulls with a force of 38 newtons, 64 degrees east of north. Nona is pulling her at a force of 51 newtons at an angle 33 degrees east of the south axis. And the third force is by Fifi, who pulls with a force of 65 newtons at an angle of 21 degrees south of the west axis. So the main thing to consider here is that there's a net force acting on Kayla, and she's going to either be pulled in, into one of these 4 quadrants here. So she's either being pulled this way or this way or this way or this way for a general direction. In order to find the equilibrant force, we're going to take that net force and we're going to flip it 180 degrees. And that's the opposing force that Kayla here has to pull with in order to remain stationary. So whatever direction these dogs are pulling her in, that's the net force, and she's going to pull in the opposite direction with an equal and opposite force, according to Newton's third law. All right, so place your hypothesis first before we begin. I want to know what force you think she needs to pull with, and at what angle, and at what direction. So east of north, or north of west, or etc., etc. So what quadrant do you think she needs to pull in to balance these 3 forces? Pause this video, make your hypothesis, and then come back. Pause it now. Welcome back. Okay, so you either picked quadrant 1, 2, 3, or 4, where you think she needs to pull with. So the first thing we're going to do is calculate the net force acting on Kayla. In order to do that, I've broken it down into 5 steps. Vector resolution, summing up the components, sketching a new diagram to find the net force. When we calculate the force and the angle, we're going to flip that 180 degrees to find the equilibrant force that Kayla needs to pull with. So let's start with vector resolution. This is resolving each of the vectors into its x component and y component. The x component for Tonto is going to be calculated using cosine of 64 degrees. Force Tonto in the x direction is going to be 38 newtons, that's the length of the hypotenuse, times cosine of 64 degrees, which equals 16.7 newtons. And this is to the east direction, which we'll say is the positive direction, west will be the negative direction, north will be positive, and south will be negative. Next, I need the x component of Nona. Now I'm going to take, the way to find the components is you take the tip of the vector and you bring it to an axis. So here I'm bringing it to the east axis, which makes a nice right triangle. And that's why I can use sine, cosine, or tangent to find the length of each. So this is the x component here, and it was 16.7 newtons. For Nona, I'm going to take this vector and I'm going to bring it to the y-axis. This is going to create a right triangle where the angle is 33 degrees. And if I want this x component here, I need to use the sine function to find that. So force of Nona in the x direction is going to be the hypotenuse, 51, that's newtons, times sine of 33 degrees. That's going to give us 27.8 newtons. Also in the positive or east direction. Now keep in mind these are adding together, so she's being pulled by Tonto and by Nona to the east with some magnitude. Whereas Fifi, on the other hand, is pulling to the west with an opposing force. I'm going to bring it here because when I take this vector to the axis, that x component stops about there. To find the x component of Fifi's force, we're going to take the hypotenuse, 65 newtons, times cosine of 21 degrees. And force of Fifi in the x direction is 60.7 newtons. Now you might as well put the negative sign there and call this negative 60.7 because she's pulling in the opposite direction that these two are pulling in. Next, we'll find the components in the y direction. The force of Tonto in the y direction is equal to the hypotenuse, which is 38 newtons, times, this is the opposite side to 64, so we're going to use sine of 64 degrees, which equals, and make sure your calculator is in degrees, not in radians. 38 sine of 64 is 34.2 newtons. And this is upward or positive. Nona's y component of her force is going to have a negative value. We're going to take the hypotenuse, which is 51, times this y component is the adjacent leg to that angle, so we'll use cosine of 33 degrees. 51 cosine of 33 gives us 42.8 newtons. And since this is downward, I'll go ahead and put a negative sign in front of there. Lastly, we have Fifi's force in the y direction. So this component downward. The hypotenuse is 65 newtons. And this side of the triangle is opposite of 21, so we use sine of 21 degrees. And 65 sine of 21 is equal to 23.3 newtons. And I'll put a negative here just to remind me that this is downward. So these two are downward, and they're opposing this upward force. All right, next we're going to take these and we're going to sum them up or add them to find out if she's being pulled east or west, and then if she's being pulled more north or more south. The sum, sigma for sum, of the forces in the x direction is going to be 16.7 plus 27.8 minus 60.7, which equals negative 16.2 newtons. So she's being pulled in the negative direction or to the west more. So Fifi's force is pulling her to the west more than the other two forces are pulling her east. Then the y components are summed. We have 34.2 newtons minus, or plus or minus, 42.8 minus 23.3. The sum of the forces in the y direction is negative 31.9 newtons. So she's being pulled downward more than she is upward. So to find the net force, we're going to sketch a new diagram. With negative 16.2 newtons, or 16.2 newtons to the west, and negative 31.9 newtons, or 31.9 newtons to the south. And the net force is drawn from start to finish of our vector diagram. I'll draw a big arrow to represent the net force. I need to find the magnitude of that and the angle of it. This is a right triangle because we sum the components x and y and they are perpendicular to each other. We can use Pythagorean theorem since we have a right triangle. We'll take the negative 16.2 squared plus negative 31.9 squared will equal the net force squared. Sum this, take the square root. The net force equals 35.8 newtons. Now we need the angle. Since tangent of theta equals the opposite side over the adjacent side, and we just want theta, we're going to take the inverse tangent of this fraction. So tangent -1 of the opposite side, which is 31.9, over the adjacent side, which is 16.2. And that is equal to angle theta. So theta, make sure your calculator is in degrees, is 63 degrees. Now for the net force, that is measured here from the west axis. So this is 63 degrees south of west. Your graph is very important because it gives you a direction. Lastly, since she's being pulled in this direction, we need to find the equilibrant force so that she can keep herself stationary. We're going to flip that net force 180 degrees and calculate the equilibrant. I'll just redraw it here. And this is 63 degrees, and the net force is 35.8. Let's rotate this 180 degrees. And using geometry, we can say that this angle, 63, is equal to this angle. Or if you needed to calculate the other angle, you would take 90 minus 63, which gives you 27. It just depends on which way you want to determine the angle. This is 63 degrees north of the east axis with a magnitude of the same 35.8 newtons. So as a result, Kayla needs to pull with a force of 35.8 newtons at 63 degrees north of east. Was your hypothesis correct? Compare. Determine why or why not. Why it was correct or why it was not correct. All right, so that is how you find the equilibrant force. This can be applied to anything from nurses applying bandages to a wound to hold the wound closed, and hanging picture frames on the wall. The force downward of a picture frame would have to equal the force of tension in the strings holding it up. That's it. Thanks for learning, and have a great day.